Hello, and welcome to our final project for MECA 482, Control System Design course. Our group members consist of myself, Crystal Farrand, Brandon Loeb, Andrew Davis, and Nickolas Hofmann. I will be introducing you to our project. Andrew will be covering the project scope and parameters. Brandon will be covering the mathematical model and MATLAB implementation, and Nickolas will be covering the Capella Sim model. Our assignment project is to utilize MATLAB and Capella Sim to create a simulated Furuta pendulum. The Furuta pendulum, otherwise referred to as a rotational inverted pendulum, was invented in 1992 at Tokyo Institute of Technology by Katsuo Furuta and his colleagues. This pendulum is often used to demonstrate nonlinear control laws. The Furuta pendulum consists of a driving arm which rotates in the horizontal plane and a pendulum attached to that arm which is free to rotate in the vertical plane. The objective of this project is to design and implement a state feedback control system that will balance the pendulum in the upright vertical position. This requires driving a mathematical model of the Furuta pendulum and a controller for the system that can be implemented into MATLAB. Capella Sim will then be used to create a simulated version of the system that can be linked back to MATLAB. Together, MATLAB will act as the controller for the Capella Sim simulation.
Before the rest of my group can walk you through the process of creating the Furuta pendulum simulation, I would like to list out our assumptions that we made while modeling the system and creating the controller. For the model, the angle theta is assigned to the angle that lies between the rotary arm and the pendulum. For the angle alpha, it is used to describe the inverted pendulum angle. These angles directly relate to the position of the pendulum at any given time. Both angles are derived taking into account the counterclockwise rotation that will result in a positively increasing angle. The counterclockwise rotation is brought on by a positive control voltage. Most importantly, the angle alpha is set to be equal to 0 when the pendulum is perfectly upright and balanced. For the controller, the dampening ratio will be equal to 0.7. The natural frequency will be set to 4 radians per second. The maximum pendulum angle deflection is required to stay below 15 degrees. And the maximum control voltage is required to remain below 10 volts. Complementary to the specifications just listed, the pendulum deflection and control effort requirements are to be satisfied when the rotary arm is tracking a give or take of 20 degrees angle square wave.
Starting with our nonlinear equations of motion, we began to break down and understand the task from a mathematical standpoint. We were given a set of files that outlined initial values to set up the Furuta pendulum. More specifically, the equations that describe the motions of the rotary arm and the pendulum with respect to the servo motor voltage, i.e. the dynamics, will be obtained using the Euler-Lagrange equations. We located the system with state space coordinates, theta and alpha, and use those coordinates to find our velocity. The Lagrangian of the system is described as L equals T minus V, where T is the total kinetic energy of the system, and V is the total potential energy of the system. Thus, the Lagrangian is the difference between the system's kinetic and potential energies. We then applied friction to the system and came up with our generalized equations, motion equations. The Euler-Lagrange equations are a systematic method of finding equations of motion of the system. Once the kinetic and potential energies are obtained and the Lagrangian is found, we computed the various derivatives of the equations of motion. After going through this process, the nonlinear equations of motion for the rotary pendulum are ready. These equations were then linearized and put into matrices. The way this works in MATLAB is through setup row pen file. The model parameters are automatically loaded using the configure servo and configure single pendulum functions. Then it calls row pen ABCD equations script to load the model into the MATLAB workspace. The state space equations will put input as matrices A, B, C, and D into the row pen ABCD equations script. When running MATLAB files, we started with setup row pen. This file configures servo, loads the rotary pendulum model, sets the basis for balance control, sets up the parameters for swing up control, and puts a high pass filter and PD control to compute the velocity. Calc conversion constants contains useful conversions for parameters needed in swing up control. And row pen ABCD equations holds our state space equations.
And finally, to test our PID controller, we used the robotics simulator called Capella Sim to simulate the Furuta pendulum. The base model of the system was provided by Professor Banks, which contained the overall geometry of the pendulum. And using this model, the exact specifications were entered into Capella Sim. Since the mathematical model used the physical properties of the system, such as mass, moment of inertia, length, and so on, this system was very sensitive to change in any of these properties. So it's very important to have the model reflect the values used in MATLAB exactly. To connect Capella Sim to MATLAB, our group used a remote API client to be able to receive data from the model, as well as apply torques to the rotating arm to eventually control movement. The API was workshopped heavily with Professor Banks within office hours over the semester to make sure the client reliably connected the two softwares together. Using the MATLAB scripts that Brandon described, live data from the model was imported, such as velocity, acceleration, and we used those values to control the rotating arm by sending movement commands via the API. To demonstrate the execution of our controller, Brandon will share a screen to show the Capella Sim simulation working in real time alongside the MATLAB scripts.
On the left, you can see our MATLAB code, and on the right, you see the Capella API running our simulation. While running, the API is constantly calculating the angle theta and displaying it to keep the pendulum arm upright. Here are our root plots. And shortly, we will have one more graph. Here's the system response.